We will talk about how computers store data in this video. Computers store informations, and these informations are digitized. As you saw from the previous chapters, right, when we talked about the concept of having assembly code, uh, converting your programming code into low-level instructions that could be understood by the machine. These informations are converted into a whole bunch of ones and zeros and this is where we get into the binary info, and that's really the concept um, of how computers store data, right? It's just how we store these ones and zeros. So if you look into computer memory, it's basically divided into very small storage locations. These are what we call bytes. Now, bytes are not the smallest storage unit. In fact, we can even break each byte up, right? So each byte can be broken up into 8 bits. Okay. And then they're basically into it. So we'll talk about this later on. But what do we do with these bits? Well, these are physical locations where we can actually store a whole bunch of ones and zeros. So you can think of these ones and zeros as, like electrical charges, right? Where you have positive charge and negative charge, or you can have a single electrical switch, right? Having it on, this means one. Having off, this means zero, right? So you can think of this whole bit, right? This whole map of bits in computer memory having a whole bunch of ones and zeros, and some of those are on, some of those are off, and things like that. And that's really how computers store informations. So let's take a look at this in a next slide. So this is how we visually represent this a byte into 8 bits. So you can look at this entire um, blue chart here is an array, right? Array with 8 elements sitting inside of it. And this information could either be ones, could either be zeros, so on and so forth. So imagine you have a, serial switches like so, right? As illustrated here. You can turn every single one of these informations into ones and zeros. So literally, I mean, if you have a byte array filled with a whole bunch of ones and zeros in this pattern, you can say this is a zero, this is one, this is zero, zero, one, one, zero, and one, right? So this entire thing basically maps into this blue charts right here. So this is an 8 switch, right? Electrical plate. Another way of thinking about it is a single byte can be stored in an array of 8 bits. Right now, we're talking about array. So this is an array right here. Right? This entire thing is an array. So what is an array? Array is a block of elements that are sitting next to each other contiguously. Okay, and there is an index associated with these because they're sitting next to each other. There's no break. There's no gap in between. Now the question comes, if we're to store a whole bunch of ones and zero in there, we're interested in how many possible value that could be stored, right, in this array. So the question is, how many, right? If you were to put, right, so one possibility is what you see here, and the other possibility is all zero, right? And then the other possibility is all one, 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 right? So you could vary these. And the number of possibilities gives us the number of integer range, right, that we can ever have, storing information into this 1 byte structure locations. Okay, so there's a lot more slides here. Let's move on to the next one to see how we do that calculation. So before we get into that, let's just recognize one thing, right? So we talked about where array is a data structure. It allows us to store one or more elements having the same data type. So basically all of this information sitting inside the array, they have to be of the same type, right? So array property number 1 is every element sitting inside the array has to be of the same data type. In this case, integer, right? So this is integer. And every single element has to be sitting next to each other. Okay, so there's no gap in between. Okay, so if this is occupying memory location 0 times FA1, the location next to it could be FA2, right? FA3, so on and so forth, right? And now in general, we have 256 6 possible values of ones and zero. Why is that? Let's take a look at it in the next slide. So, and this is how we compute information there. So before we compute the number of possibility, which is 256, let's see how we can compute this, right, into a decimal. So the way that we do that is we will assign a binary, right, value next to each of these bits. So the very first one is 2 times 0. The second one is 2 to the 1, right, 2 to the 2. As you can see here, if we were to map this out, what would happen is this very first one is going to give us 1 times 2 to the 0, which is 1, right? Because any number to the 0 power is 1. So this is 1. And this one is going to give up, because this one maps to a 0. So this means 0 times, right, 2 to the 1. So what is this? 0 times anything is 0, right? Okay, so what about next one? The next one is 4, right, times 1, right? So I switched it. So this is 4. And the next one after that, this is 2 to the third, and 2 to the third has 1 in it. So this is 1 times 8, right? So this is 8. And so on and so forth. So the very last one is 1 times 2 to the 7, right? Which is 128, I believe, right? So if you were to map everything out, and we don't care about zeros, right? We only care about 1, then this gives us a number, and this is a decimal number, right? 157, right? So we add them all up, right? All these ones. So 157. So this is what we call binary number, okay? Binary number. And this is what we call decimal number, okay? So therein, if you have a switch looking like this, this is a binary representation of 157 in decimal. So that's how we represent numbers, right? Okay, now what is very interesting is, let's just say if we turn every single switch to on, right? So in essence, you will have 1/8 next to it, right? This should give us the biggest number possible, right, in this representation. And the smallest one possible is all zeros, right? So we got a range. This is the smallest one. This is the biggest, right? Smallest and biggest. So what is this number, right? And what is this number? Then we can see the total number of possibility that could ever exist, right, in this 8-bit switch. So let's look at the next one, because I have several more illustrations here to see it. So this gives us, if for a 1 byte, right, switch, the largest value that can be stored in a byte is 256, right? So if you add them all up here, 2 to the 8th is actually 256, right? But because now we're talking about 0 being one of the values, right? So 0 all the way to, right, you have a 0, you have 1, you have 2, right, all the way up to 256, 255, right? That represents a total of 256 variations. So the biggest value, right, we're talking about the largest value possible, is 255, right? 255. And the larger values are going to be stored in 2 bytes, right? What is 2 bytes? 2 bytes, 16 bits, right? So now this is further expanded. And this is what you're looking at here, 16 bits. It's got 2 bytes. So this is the first byte, and this is the second byte, right? So if you add them all up, right, eventually you get 65,535. So this is a very, very large number, right? This means that in a 2-byte memory, the largest value you can store is 65,000, right? 65,000-ish. And it goes all the way from 0, 1, 2, 3, all the way to that, right? So this means, as the number of bytes increases, the number of very integral value that you can store in this data structure will go up exponentially, right? So for example, if we're talking about integer, okay, integer is 4 bytes, right? This means that you have how many data possibilities out there, right? 200. So int, this one is 4 bytes, right? So this is 202 to the 32, right? Why? Because 4 bytes equates to 32 bits, right? So this is a number of different values you can have here. The biggest value inside that turns out to be 2 to the 32 divided by 1, because you have to account for 0, right? This is signed, okay? This is signed range, but in the unsigned, then it's half that. So I'll get into the difference between signed and unsigned later on. But that tells you, the storage capacity of a computer, right, in terms of bits and bytes. Now, if you look at bits and bytes, here there's a table here that illustrates in the 64-bit, right, this is 8 bytes. You can store roughly 18 different, billions. This is the very, very large storage structures. And these informations are very capable of being held in a computer. Now, if you're wondering the size of these various data that we talked about, data types, well, we have char, in, string. You can use what's called size of. This is a C function. Okay, this is a C function. You can simply just invoke it. You can do a C out, right? Size of, and you can type in, the data types in this case, char, and this will give you 1, right? This might be true, and this might be true in your current computer, but years ago, 20 years ago, this may not be true. So if you have a very old computer, that computer has, assuming C libraries on it, you can do a size off and you can see different numbers. So these are the numbers that are true in contemporary computers. So if you do this, you might get 8 or you might get 16. Okay, so it differs. So try this out and see what you get. So this means long. L means long. F means a floating point. String is a C++ string, which is a class. This turned out to be 24. Okay. All right. So this concludes our discussions on how computers store data.